maybe table logic or using the like rate over rates equal to K concentration over K concentration. Remember the ugly algebra method? Okay. Well, maybe you need to review pieces of that. Okay. All right, so I'll explain the homework in a second. So today we're going to be talking about reviewing the homework real fast, talk about the CV lab, who's done with that, like to the extent that they can get done. I saw a lot of people editing yesterday. Okay, so I'd like to be able to start looking. I've got 2 online labs still to grade because I've finished those. Took me a little while. But CV lab, I'll tell you what I specifically need from you by tomorrow. And then we have mechanisms to go over. It's pretty easy. It's actually one of the, I think it's next as a whole. And then we're going to start our problem set and kinetic or mechanisms today in class. We're going to try to knock out our multiple choice in class. I'm optimistic. Okay. So here's what I need from you. I already had a couple of you guys ask some specific questions about the CV lab, but just a quick question. Does anybody know why we're ignoring the sodium hydroxide? Yeah. JG. Okay, so it's clear, so we can't really measure anything with it via the colorimeter because it doesn't have any absorptive values. So that's like by the nature of the technique we're using, we have to ignore it. But does its concentration change over the rate of the over the duration of the reaction? It does, right? Okay, so it actually does. But by how much? Say again? Very, very, very little. We started off with like, what was it, 0.2 molar? Okay, so you put 0.2 molar in. What was the concentration of CD that you put in? Say again? So it was 25 micromolar, but you guys, you know, by the addition of it to the sodium hydroxide, even diluted it a little bit more. That's just because of the nature of the water in the sodium hydroxide, but you reacted it. So we had this 25 micromolar, which is 0.000025 molar, compared to 2 molar. I mean 0.2 molar. Okay, so if you did the VBA, which you had to, I think was number 3 on the pre-lab, that was like the 1,000 to 1 ratio, and then like a 1 to 1 ratio. If you're 1 to 1, it would be an appreciable amount of concentration that was changing over time, but it wasn't. It was still like over 1,000 to 1 ratio, or about 1,000 to 1 ratio. So there was not an appreciable change in sodium hydroxide at the time. So we just kind of ignored the fact that its concentration was changing because that was not specifically what we could measure, and 2, it wasn't changing appreciably over time. So we looked at the one that was changing over time to determine the rate of that, or the order of that. Okay, so it's called flooding or swamping the mixture with a really concentrated version of one reactant and a low concentration of another reactant. So you can use the word swamping or flooding the reaction in your analysis there. Okay, so that's what this is right here. In terms of like the way it's phrased, it's not just a rate law constant. It's called the pseudo rate law constant because we can't claim it as the rate law because we're excluding its other reactant. So the pseudo rate law constant or pseudo rate law is technically what we're finding. Cool? Okay. So what I want from you tomorrow, can I take this down? Okay. What I want from you tomorrow is for you to, like, first thing right when you walk in, write down your order, your rate law itself, the Lin-Reg equation that you associated with that rate law, and then the half-life. Okay. In your Lin-Reg equation, I'll be able to see what? Your K value. Which part of the Lin-Reg is your K value? The slope, so the M. Okay, so I'll be able to compare it from there, and then tomorrow I'll tell you the real deal, and then you guys can do percent error from there. Questions? It just means that it's not the real deal K value because we've excluded the sodium hydroxide. So by nature of excluding that, we can't call it the K value for that reaction. We're calling this the fake K value just specifically based on the data that we were able to collect from that reaction.
And we can say that because we thought.
Yes. Yes. Okay, so questions on CV? Okay, knock that thing out when you can. All right, here we go. I have the whole entire thing on here, so let's roll. I'm not going to spend like ton of time on each piece because some of it is repetitive though, so just beware. And then note this on your paper someplace to yourself because I finished making the test, and I do want to make sure that there's a full disclaimer. Occasionally, instead of using concentration, because concentration is just molarity, like molarity in the solution, so moles per liter, gases don't really dissolve in solution all that well, right? So I could give you the concentration if a gas dissolved in solution, but the same thing, or the equivalent concentration for a gas is partial pressure. So if I give you partial pressures in a table or on a graph, they work exactly the same way as concentrations do. So do not let that scare you. It's the same dang thing, okay? Now, so if concentrations and molarity, what would this probably be in? What do you guys say? Say again? Pressure, guys. I heard atmospheres, thank you. It could be in kilopascals, it could be in millimeters of mercury, but it's probably going to be atmospheres, because that's our standard unit there. Questioning yourselves. Okay. So in the first one, so I have like kind of all my work here, so I'm going to scroll down some. But in the first one, it has to determine the rate law. They gave you all the graphs there, right? Yes? Okay, note to self. Sometimes in an FRQ, you'll be given all the graphs, because sometimes it's too time consuming to put everything in L1, L2, go back and regurgitate it as a natural log and then 1 over. So they want to know that you can apply that knowledge, so they gave you the graphs in this one. Expect one like that as an FRQ. Okay? So as you looked at the R squared values for all of them, you were able to determine that this was a what order? Second order, just by the nature of how best fit it was. And then since the slope in our, yeah.
Oh, I'm just wondering, how do you, so like if it doesn't specifically say integrated rate law, it means different?
It does, yes. If it does not say integrated rate law, it just says rate law, you just understand to be rate is equal to K, concentration or whatever. Good question. Okay, so here, knowing that it's the second order reaction, what is the integrated rate law for a second order reaction? 1 over A final is equal to, so is it positive or negative? Positive, right? So there's our K right there. So how do I know our K? Look at the slope. So that 0.0142 is the K value itself, but it doesn't have the units on it. You have to understand how to put your own units on it. So we know it's second order. We write the rate law according to this, what was it, butene? And that's second order. So here's our integrated rate law. So that's just a reminder. K is our slope. So the slope is being 0.0142. If it's second order, think about it. This is molarity squared, right? So how do I get molarity squared to just equal molarity per second or per time? I have to divide by what? 1 of the molars, right? So that's why I just put molar per time, because it didn't give you a time specific unit, so I just put seconds here for my own purposes, but you could just put per time as well. Questions there? Okay, graphical analysis is important in terms of like, if you're given the information, you don't have to do the calculations, you should be able to pull from a graph really simply. And then it said to solve for the half-life. So if you were given a value of second order, do you have this equation memorized? Almost, okay. 1 over K A initial. So they gave you an A initial in the graph. I'm sorry, yeah, in the table. So taking that table value, plugging it in with the K value you just found, notice that molarity and molarity cancel out, so we get time, and I just put seconds. You could have put minutes or hours, but something like 4,401. Okay, give me a thumbs up. Can I move on? Okay, so it's just really the using of the use of the half-life equation. Okay, so for the second example, they gave you reaction, a table with instantaneous rate, these concentrations, time, and then concentration. So given all this information, they wanted you to tell them how to find the reaction order. Can somebody give me like one generic explanation? I can do hard names. Thanks, JT. Okay, so their linear regression of the 3 varieties of comparison to time determine which linear regression was the best fit based on the R squared value. Okay, so we're trying to put this together in like 1 or 2 sentences. I'm not grading paragraphs. I saw some people with paragraphs. Okay, we don't want to have paragraphs on our tests and stuff, okay? So graphical analysis using integrated rate law. What was another way? How do you want to use the table? So you're looking at the concentrations and the time. I'm sorry, the concentrations and the rate?
Yeah.
Okay, so kind of using table logic. And a lot of you guys are not as comfortable going up the table, but it works the same way. So if I went from 0.5 to 1, going up the table, what happened to concentration? It multiplied by 2, right? So it doubled. What happened to rate? It doubled. So I know we've always like looked at trial 1 down, but you can always go back up if you need to. So yeah, you can use table logic, and there's one more. Anybody? Emily? Potentially ugly algebra, which is the algebraic method of using the table. That may be kind of too similar to the table logic though. Okay, so table logic is the term that we use, so just make sure you're specifying like what variables you're plugging in and so forth. And ugly algebra is another term that we use that we're not specifically going to put on FRQs. All right, so using the table data, you could view, I put slope, but R squared value of the concentration versus time. This is that linearity one that JT was just talking about. And then we could compare, this is kind of that ugly algebra method, which is the table logic. So basically we're looking at the comparison between how concentration changes and how does that impact the rate. The way you can prove that is this nice little setup. You can do rate 1 over rate 2 is equal to concentration 1 over concentration 2, or vice versa, 2 over 1, whichever is larger. So for example, what was it, point 1? Yeah, so 1.0 and 0.5. Okay, so for this one it was 1.0 molar over 0.5 molar, and the rate was like 0.0006 or something like that over 0.0003. I might be off a 0. These were molar per second. So basically this is what over what, when you divide, what is this? 2, and this is equal to 2, right? So this is concentration to some power. So what's x? X is 1. So you can do a real simple explanation mathematically, because most of you guys are probably more comfortable with this anyway, versus explaining. When the concentration of trial 1 doubles into form trial 2, the rate then doubles, like it just starts to get jumbled and you're starting to explain it. And then this is the one piece that not everybody's going to be comfortable with, but explaining how instantaneous rate, like at a specific time, can be compared to another instantaneous rate at a different time. And so you're doing the same thing. You're looking at the instantaneous rate, so you're essentially just finding rate, but at a specific concentration in time. So it works the same mathematical way, like this, but you could find it yourself from a graph. You could look at the slope of an instantaneous point on the graph. So it's actually utilizing the graph this time, not the table. That's how that's different. Okay? Okay, and then what was the next question? My board's doing funny. Okay. 2 different methods in which you can find rate constant. So we know one of them is what? Finding slope, right, of the most linear relationships. The other way? Okay, so you can plug it into integrated rate law if you have that, or you can plug it into the rate law itself if you have the rate law itself, right? So there's actually a couple ways. Or you could, if you had half-life, you could find it via half-life. So using integrated rate law on this one, I think this was first order, so that's why I use this. I could be wrong, but I think this was first order. So using the slope, right, from the integrated rate law itself once it was graphed. You could use a half-life equation if you had everything, like if you had the time of half-life. And then again, instantaneous rate, once you found your own instantaneous rate. So once you found your own instantaneous rate, that would be a rate. Oops, that would be a rate. And then finding the concentration at which that occurred, you could plug in that, you could plug in this, and you could solve for K. That was given a graph though. Now remember, it's not instantaneous rate of the ln graph, it's going to be instantaneous rate of which graph? Which graph will give you rate? What versus what? Concentration versus time, right? So not always are they going to give you the natural log and then 1 over, it's going to give you concentration versus time. So if you had like a graph like this, and you had to plug in a point, you find the point in time, draw your tangent line to that, and then of that line, of the tangent line, that would be the rate, because that would be the change in time at that specific instant. And then the last question I could think was to find how would you find half-life? So for this one in particular, first order, this is on your reference table, right? Okay, so don't worry about memorizing that one so much, it's there. You could use that, or you could read from a graph. You could read from a graph like concentration versus time. How could you find half-life from this? Any takers? The time it takes for the what we have. Concentration to go to half, right? So let's say we have concentration 1 here, and half of concentration 1's like down here. Kind of a rough estimate. So here's the time it took for the concentration to decay to half of its initial concentration. So this would be T1/2. Graphical analysis is important for your test. Just making sure you're clear here. Next, and I think almost last question. Okay, so we're looking at this reaction. We've seen this reaction before. Yeah, question? Mm-hmm. Question on the second question here.
Yeah.
The concentrations are negative.
Yeah, like on the graph here.
What was it, ln though?
Yeah, those elements.
Okay, so that's not really the concentrations being negative. The natural log of the concentration is negative. The mathematical relationship with natural log becomes negative quite often.
So if you're trying to find the half-life,
You can't do it from that graph,
so I
period.
put it back to the calculation.
Um, if you had the graph concentration versus time available to you, you would use only this graph, and this is very important. Only this graph you can find half-life directly from it, because it's concentration being halved over a certain amount of time. Drop your little data point down, and that is the T1 half. Vice versa, if you had like an actual log graph, I would just find ln of 2, which is 0.693, over the slope of that graph, which would be the k. So I wouldn't even try to find it graphically. I would just use the slope, which is the k value. Okay. All right, the last piece. We've seen this reaction before. There's a decomposition reaction. What's happening to the spontaneity here? What's happening to the disorder here? It's increasing, so what's your delta S value? Positive or negative? Okay, this is a quick review. So S is positive. If it's occurring, it's actually happening, guys. What's the delta G? So what do you mean by negative delta G? What's the term we associate with that? Thermodynamically favorable, also known as spontaneous, right? Spontaneous is not the term for S. I know S and S are like, it's the same letter, it doesn't matter. Thermodynamically favorable, delta G. Disorder is delta S, and then thermochemistry, the delta H is what? Enthalpy, right? So if I had some other data up here, you could then find the delta H. Why am I reviewing this? Because things are going to start being like just a little bit cumulative, and we'll talk about the graphical analysis part of this, like on the reaction diagrams. So what's a reaction diagram look like? Draw it in the air for me. Reaction diagram. What's a reaction coordinator reaction diagram look like? All right, so we're just drawing little curves in the air. Good job. Okay. So it looks like this. Well, isn't this like a way I could find activation energy? Okay. So where is it? So let's call this A. Call this B. We'll call this C. The activation energy is the difference between what and what? A and B. Okay. EA. And what's the enthalpy value? C and what? C and A. Okay. So like from here to here. And then what's the activation energy of the reverse reaction? C to B. EA. EA prime was the reverse reaction. So, I mean, if we're talking about graphs like this, you better bet I'm going to ask you for delta H. Okay, is it an endo or exo curve? Exo, because products are lower than reactants, meaning they have released some sort of energy. Okay, so back here, no, it's right here. Okay. I was like, just skip that question. All right. So in this one, two methods that you could use to determine the rate law. This is redundant now. Plot your data, find the best fit through linear regression. Use instantaneous rate to do concentration changes over time. So that's our rate 1 over rate 2 is equal to concentration 1 over 2. How do you find the order from this? You just divide. You put this to the x power, solve for x. Okay. So a lot of times you can do it right in your head. You don't need like a calculator for those. From the data given, so the time data. Actually, let's look at this. Let's look at this really closely. Hold on. I thought I could do this. Let's see here. What's the approximate half-life given this data? Can you guys, let's see here. So it's between here, 800-ish seconds, right? Okay. And then another half-life would be us taking from this, let's pretend like 0.5 is between here, because we're starting at 1.0 molar, we're going to 0.5 molar. What would be the next stop point for half-life? 0.25, which is kind of between here. So this is about 800 between here. What's right here? About 1600. So do you see the half-life is 800, 800, 800, 800 each time? Okay, so you could look at half-life. If you had a better table, it would be super easy. This is not an easy table because there's no exact halves at every time. But you also had all this other data, which is why you actually probably did not use that table. You used the graph. So first of all, given the fact you had all those equations given to you, write the rate law. So we had hydrogen peroxide to the first power or first order. Find two methods to find the value of K. We already know all those, we just discussed those. What are the units of K? If it's first order, there's no concentration in it, it's just per time. So in this case, I just put per second because I needed a time unit. So concentration is not in the K value for first order. And then given this graph, so this is just what I drew on the board earlier, concentration 1 to concentration 2, so from 1 to 0.5. What was the time it took to do that? Boom, between what and what? 800 and 1,000. So as long as your half-life is, if you estimated it to be between 800 and 1,000, and then you mathematically derived it using the half-life equation 0.693 over K, plugging your K value in because your K came from your what? Slope. Well, it wasn't on this graph, but it was someplace else. Where did we get it? I don't have my full question up here. Any takers? How do we find the K value there? Didn't it gave you the, thank you, I don't have those graphs copied up here, but you guys see them on the very bottom right hand corner of your paper. They gave you the slope, so that's the K value. 1 second, JT. So given that K value, plug it in, you get 866-ish for your half-life, and that matches with what we graphically analyzed. Question?
Does the K value like affect symptoms? How do you say that?
It's difficult. Sometimes, like, usually your M value, which is your K value, is just a line of numbers, right? So I'm usually between 3 and 4, just to stretch them out. And they probably would not take off for sig figs, as you guys probably see on your test. I've limited the chances I have taken off points for sig figs. Because all of our data is just between 3 and 4, actually all these are 3, then I would stick to around 3. But all of these, I mean, actually those are 2. There's no decimal. But the thing is, it's over time, and so it's a continuous amount of sig figs. Okay, yeah.
For the last one,
Yes, that is the only graph you can use to find half-life. That is it. You cannot use LN graph. You cannot use 1 over time graph. That is the graph. Are you talking to me now? Because I think you have to speak louder.
then you also had a order 1,
Yes.
so you use the concentration.
So that's the point. I use the LN graph, the 1 over concentration graph, and the concentration versus time graph. I use the comparison between all those to figure out which order it is. The LN graph was the most linear, and I'm not sure I have that up here, but it's on your guys' paper. Yeah, so I didn't copy all those graphs here, but the LN graph was the most linear, therefore it's first order, right? Done. I don't need to discuss order anymore. But to find half-life, I have to use this graph because it's concentration going half over a specific time. Do not do integrated rate law because of that. Okay. All right, I'm done with this. We're gonna move on to mechanisms. Okay. I think I have copied a little bit there for you, just a little bit. In your NMSI reading, you guys only read the page 12, right? Okay. Feel free to read more. I'm not going to require you to read a certain amount. It's good for study evidence. Like, it's good to go back and review those. You guys know those questions have answers to them, so I'm not going to go back right now and require you to go back and do all those questions, but I do think there's some valuable ones in there to look at before your test. So these are just a couple of thoughts. I think these were past the pages that you guys had to read, so I'm not going to do this as a warm-up. These are past the pages you had to read, so I'm going to move on, okay? All right, so read this purple stuff first. Read this first, and then we'll talk. I did copy some lecture notes for this, just not this side, because I have the problems on there when we get to the problems. Just have the problems. All right, please, you had to summarize what a mechanism was. What is it? Don't read it verbatim, please. Steps it takes to make a nuclear reaction happen, right? Doesn't matter how many steps there are. It can be 5 steps, it can be 2 steps. It's independent, really, of the number of steps it takes. There's only one step that really slows down your reaction. Okay, does anyone know the name of that step? Rate determining step, right? The step that determines the rate, right? So we talked about the slowest person on the IM or the relay team, right? That's the rate determining step, okay? So the mechanism that we're going to propose is just a series of steps that it takes to make the reaction happen, but like you can see here, there's many steps for bond breaking, bonds making. If I'm bond making, am I am I getting rid of reactants or forming products? Forming products, bond breaking is, or breaking reactants, right? So we're not, don't reverse it right now. Okay, so there are three things that must be true. Experimentally determined, everything has been experimentally determined thus far. And that's not something you always have to state. It's assumed that's experimentally determined. I'll explain what this means a little bit on the next slide, but it must match the overall stoichiometry. So we have a series of steps, but they all must collectively together explain the main reaction. Okay, this will make more sense when we do an example. And then the rate determining step, or the experimentally determined rate loss step, must match stoichiometrically, or molecular. There's two words for this. The BCE coefficients is what I mean by the word molecularity, but the number of molecules reacting must match. So we'll talk about that more in a second. So we have these delineated in more detail on the next slide. Okay? So as you can see on the bottom down here, this is the reading. This is the NMSI reading. So all of this data, or this information, I just kind of pulled from here. So that's why I think it's good for you guys to go back and read a little bit more of that. So we did talk about catalysts a little bit. We're going to talk a little bit more today. For the very last page of the NMSI reading, which I'm going to pull up here at the end of class, it's a really good one to go back and read. There's only one page. I think Gabby was telling me, she was like, I was reading it, and I had questions. It's like, we're going to talk about it later. But the catalyst piece of that is a good one to go back and read on. So just remember that catalyst, are they utilized in the reaction? Are they utilized? Yeah, like they're used in the reaction. Are they used up? No, because they're not changed over the course of the reaction. So they're going to go in as a reactant, and they're going to come back out as a product, unchanged. Same amount, still looks the same, and so forth. So the only thing that's kind of weird is, we say it's not used up in a reaction. Do you write this piece right here down? Catalyst can appear in the rate law itself. Because, like I said, some like zero order reactions, the reactant concentration doesn't matter, but the catalyst might. So there's some things where we will have a catalyst in the rate law. And all that stuff I just had up there, I have on the next slide too, so don't fret. So who knows a catalyst like in the real world? Say, iron for what? Luminol. Okay. Anybody else? Impact of biology. Yeah. What were you gonna say? That's just energy. That's just heat energy going in. Yeah.
Enzymes?
Different enzymes in the body, right? Who's ever heard of catalase? Who did like the liver lab in biology? Like you put liver in a test tube and it bubbled up with hydrogen peroxide? No. I mean, I did that when I taught biology. So, yes, okay. Well, okay, never mind. So, all right, so there's lots of catalyst in your enzymes, aka catalyst, in your saliva. They break down different things you eat. So what do you think breaks down proteins? No, amino acids are what make up proteins. Okay, proteases. Have you ever heard of proteases? Remember, they all end in ACE. So like catalase, protease. Who's ever heard of amylase?
Yeah.
Amylase, you spit in a cup, that's amylase. It breaks down carbohydrates like starches into smaller monosaccharides. Lipases, what do you think that breaks down? Fats, right? Lipids. Okay. There's a lot of proteases, lipases, and amylases, different forms of them in your saliva, which starts to break down the food, and then they go to your stomach, and then the stomach acid attacks everything, it rips it apart, and then there's more enzymes to kind of carry things on. Okay. Fun facts about catalyst. Yeah.
So is the catalyst just like the opposite of a rate determining factor, or like can the catalyst also slow down a reaction, or would it reverse the
It would only allow for an alternate pathway to speed up the reaction. Okay. All right, these are the definitions. These are the terminology pieces that are kind of key for kinetics. I would read and write down the things you need. I'll be quiet for a moment. Definitions are key here. hopefully you're trying to simplify a little bit as you write. No, just a little bit. So if I were writing an intermediate, I would say it's produced and then consumed. Okay, so it's a product in one and then a reactant in another step of reaction. An elementary step is just one step of the mechanism. Now there's some rules with the elementary step, but be it that it's one step of the mechanism means I can have many, many, many elementary steps in a mechanism. But if it were the special step, if it were the step I was going to write the rate law from, I can use the molecularity. I can use the coefficients from that BCE and then call it the rate law. And this will make sense when I do an example. So molecularity of an elementary step is the only thing that you can pull coefficients for. RDS, or rate determining step, is the slow step. That's probably all I really write there. Just need to take that off. Okay. Molecularity, we keep saying this, but it's just it's a coefficient, or it's a number of molecules of that step. So it's a number of molecules. And then a catalyst, we know kind of what it is, and that it can't be consumed, and that it helps speed up reaction. But when I look at an elementary step, when I look at a mechanism, I should be able to determine what's a catalyst by the fact that it's going in and it's coming out. So it's going in as a reactant, it's coming out as a product. So reactant, early step, product, and later step. Can't really shorten that too much. Yeah. No, a catalyst is it's the opposite definition of an intermediate. Intermediate is produced and then consumed, meaning it's produced as a product, consumed as a reactant. A catalyst goes in as a reactant, comes out as a product. So they're opposites in the nature of how this looks. Okay, so we're going to look at some reaction mechanisms and identify these pieces. And that's kind of where the most of our time will be spent right now. So I have submitted like another example down here. It doesn't have the intermediates, it doesn't have the catalyst and so forth on it. It's just an example of how these reaction mechanisms can look graphically, like we have here. So you can have an easy one like this with a single step. You'll notice it's a single step because there's a single hump there. Or you can see that there's a more complex one. How many steps are happening here? 2, right? So reaction 1, reaction 2. This has 1 elementary step, this has 2 elementary steps, but it's just single steps of reaction. And then we'll talk about what we can identify from those pieces. Okay? Okay, so these are the purple writing I had earlier. I was like, I'm going to have it up here again. These are the 2 criteria that must be met for a reaction mechanism to be viable, to be potentially true for a reaction. So what we'll say is, I've done an experiment and I have an idea of how this reaction is occurring in solution. And I think it takes this step and this step and this step, but we can never really prove a mechanism. We can only say there's evidence to support this mechanism is true. So these are 2 evidences that would say or suggest that a mechanism is true for that reaction process. So if you can say all the elementary steps, doesn't matter how many you have, but all the elementary steps sum to equal the overall Bounds chemical equation, then yes, this mechanism is possible for this overall reaction. So remember in Hess's law where you had like A plus B yields C, C plus D yields E, we had all these reactions, we would cancel things on left and right? Yes, you can do that, the same process here. So you could cancel C with C and then sum them together to be A plus B plus D yields E. So that's what I mean. You could sum them up as you did in Hess's law. So that's the first one. That's the first criterion. The second criterion is that if you had the rate law, your rate law would match the slowest step of the reaction. And what I mean by match is that if I had a rate law, like rate is equal to KO2 squared, what is this telling you for the rate law that the reactants are of the slow step? Well, it's telling you it's second order with respect to that elementary step, but who are the reactants? 2 O2 molecules, right? So the reaction would be O2 plus O2 yields O3 and like a free radical or something. But it doesn't matter. As long as these are the reactants of the slow step, you're showing it to match this because there are two oxygen molecules. So I mean that the molecularity of the slow step, meaning the coefficients of the slow step, match the rate law itself. And that's just a reminder here that our slowest step is our rate determining step because we can't be any faster than our slowest step. So that's why it's called the rate determining step. So in a realistic reaction, usually, back up. What makes an effective collision? There are also two criteria there. William, give me one. So there's enough energy in the collision to meet activation energy. So you have to pull all that together. That's one criteria. And then another?
Orientation.
Right. So those are the two factors to make an effective collision: orientation and meeting activation energy. So, you know, sometimes you're talking about orientation and collision. Well, you're thinking there's at least two reactant molecules that are reacting or colliding. Well, there's actually a case where you can have a or a unimolecular reaction where it doesn't really collide with another reactant. The unimolecular step is something where the molecule of the reactant is just flooding with background stuff, like solvent, like water, where water is not really the reactant, it's just there as a delivery method to get the reaction happening in solution. So in a elementary step, we will call each elementary step differently based on the number of reactant molecules there are in each step. So if there's only one reactant, we would call it a unimolecular step. If there are two reactants, we would call it a bimolecular step. And if there's three reactants, termolecular. And these are just the number of molecules in a step. The one that's very rare is the termolecular, because think about it. If you have two molecules coming at each other, they could collide in the correct orientation and totally make that reaction happen. But it's rather difficult to get a third one coming in to collide with this one and get the third one colliding in just the right orientation. It's just too difficult for a reaction to coordinate. So that's why we don't see those too often. Kiyoki? Thumbs up, people? Give me something? Okay. I'll tell you stretch break in a second. Monday morning. Ooh, that's rough. Okay. All right, so I think this is where I pick up on your notes. Can you guys double check that for me? I'll pick up on the examples, which should be here. It's the upper upper left-hand corner of back of the piece of paper. Okay. So here's what I mean by mechanism steps. The two criteria are one, what? The sum of the elementary steps, which equal the overall reaction, and two, so the experimental rate law must match the molecularity of the, which also called the rate determining step is another way to call it the slow step, okay? Because you'll actually a lot of times begin the word slow. Okay, just making sure we're on the same page here. Okay, here we go. So this is the proposed mechanism, step 1 and step 2. I want you to tell me, based on this reaction and this rate law, is this a viable mechanism? So here's how you would process it. You would say, first, I have to make sure that the multi-step mechanism equals the overall reaction. So all you do is put a line under it. Let's add these two up. So who can you cancel? That's the same on both sides. Nitrogen dioxide, and nitrogen trioxide. Anything else? Nope. Pull it all down now. Okay, so NO2, nitrogen dioxide plus carbon monoxide, yields nitrogen monoxide and carbon dioxide. Okay, so this is the overall reaction. Does it match this reaction? Yes. Okay, so once you've added them up, you're saying matches the overall BCE. Check. One criteria has been met. Okay, the other criterion is the rate law has to match the slow step. So it's telling you that this is the known mechanism. So looking at step 1 and step 2 and the rate law itself, who has to be the slow step? Step 1 or step 2? Questioning yourself, as I see. I'd say it louder, prouder. Qui, louder. Okay, so is it just Qui that says step 1? I heard a lot of you say it, be like, what, step 1? Yeah, look, NO2 squared, that means I have how many reactant molecules of NO2? 2 of them, and that matches this right here. Now, the fact that I've canceled it out doesn't really mean I've canceled it out. I just was basically simplifying the mechanism steps into one reaction. So this whole canceling is not really canceling. I'm just saying canceling in quotation, or it's simplification. Okay, so that's what we're actually doing here. So this right here matches with this right here. So this one right here, this step 1 must be the slow step, rate determining step. Yeah. If it was first order, it would not be a viable mechanism because it wouldn't match any of the steps. Yeah.
So the 2 NO2 is in the step 2 instead of step 1 would still be okay.
Yeah. If these NO2s were if this was flipped basically, I would call the second step the slow step, not the first step. I'm just matching it based on the coefficient here and the molecularity denoted here. All right, so is the based on how we've kind of described it, yes, it is a viable mechanism because the overall matches with the overall, and this I'm denoting this as a slow step because it does exist here. And then I want you guys to tell me who are the intermediates. Shout them out, come on. Nitrogen trioxide, so it's formed and then used. Okay, so the green stuff is the intermediate. So NO3 and NO3, are there any other intermediates? I'm not forming anything and then immediately using it, right? So like this is the only other thing I formed. Do I immediately use it? No. So that's the only intermediate. And then who's the catalyst? Who? So I heard NO2. Good. So it has to be used as a reactant and then pooped out as a product, right? Because you can't have it being used up at all. Yeah.
So if you can't have an intermediate like simple reaction, right? Just one complex elementary.
Correct. Right. So in a single elementary step, via the mechanism being it's only one single elementary step, there would be no intermediate. Through a series of steps, you would have many intermediates. One second. So NO2 here means that one of the NO2s is a reactant, the other one is a catalyst. So it doesn't really matter as long as you see it here and then form as a product, means that your NO2 itself is the catalyst. Question, Darcy?
Is it possible to have more than one intermediate?
Yes, and especially if you have a series of steps. All right, we're going to do another example quickly.
Would the rate law of rate determining step change the basic coefficient on the
Yes. If there were like a 1 and a 2, that would be overall third order, so that would have to be third order after. Quick question, yeah.
Do you have multiple step reactions but no intermediates?
Probably not, because something has to feed the next step. Okay. All right. So speaking of, I want you to turn and talk right now. Looking at this, let me maybe make this a little bit smaller. I think you guys can see all that. Tell the person next to you everything you know about this reaction. All right, come back to me. Come back to me. 3, 2, 1. Niall, give me one thing you know. Okay, overall it's exothermic. Good. Jaden, give me something else you know.
There are 2 steps.
2 steps. Emily, give me something else.
The activation energy is higher for the first.
So the activation energy of 1 is higher than EA2. What does that tell you about 1? Come on, that's mine. That is the rate determining step because it's going to take so much more energy and time. It's going to be really slow to hit this peak, but it's like really fast on the second peak, so it's going to be a fast step on number 2. So 1 is the slow step. So therefore, if I knew these reactants here, what would I also already know? So I would know the rate law because if this is these are the reactants that feed the slow step, those are the reactants that go in the rate law. Period. Okay. If I were to catalyze step 1 or step 2, which would I probably catalyze? Step 1. Step 2 is already fast. I don't need to catalyze it any faster. I need to target the catalyst to catalyze the slow step so that it would have a lower activation energy but then still follow the same path on the way out. Okay, I think there's one more thing. How many intermediates are here? Okay, so we said there's 2 elementary steps, right? So I have these reactants, I form this little transition state, and then I form a intermediate that's now going to be used, so it's produced and then used as the reactants for the next series of steps, or next step in this case. So there might be 1 or 2 intermediates here, but there's 1 set of intermediates. Okay, good. All right, so let's look at this example. It's given this reaction and this rate law. This is the suggestive mechanism. So like we have an experiment, we've suggested this to be the mechanism. Is it possible? Go. All right, is it possible, yay or nay? Yes, it is. Okay, so what were the 2 criteria you proved, or tried to prove? Support. Go, William, give me one. Okay, so if you were explaining this on an FRQ, okay, if you're explaining this on an FRQ, you have your series of steps, right? You've already just kind of canceled out the, not spectators, things that cancel. So what are you canceling? Okay, so the fluorine and the fluorine free radical or something like that. And then so what do we sum to?
So we sum to 2 and 2.
Good, so we just kind of pulled this one and this one together. Whatever that is, right? Okay. So then once you have shown this through the cancellation process, you're going to say this matches the overall. And we probably would write out equation, not like BC, like on the real deal, but I'm okay with your NBC for me. So this is just a reminder we're matching with that equation, so we're good there. Megan, what's the other thing we have to state?
That the rate law matches the
I'm going to say, yeah, so put that word in there someplace.
The rate law matches the molecular weight.
Okay, so the rate law matches the molecularity of, I'm going to say of the slow step, because that's how it's denoted here. And then in parentheses or something, you put like rate determining step, just to clarify that that means the same thing. So what you're looking for is 1 NO and 1 fluorine, because they're both to the first power, and then you see here there's 1 NO and there's 1 fluorine, both representing a 1 coefficient, which means to the first power. Okay, so that's what we were showing is 2 criteria being met. Moving on, yeah.
Can we check the sign criteria being met to get to the power? Or then you just put the reactants?
Yes, because remember, rate is determined by the reactants colliding to produce the products, which we don't really care about at this point, but yeah, these match those. Okay. All right, next one. Determine the intermediate and if potentially being a catalyst. Taz, give me one of them.
Catalyst is nitrogen monoxide.
Okay, so nitrogen monoxide shows up as a reactant. It's going to be then showing up as a product. So since it was never consumed and never really used, NO is a catalyst. Good. CJ, give me something else. So nitrogen dioxide is produced and then immediately consumed in the second step, so it's our intermediate. Okay, so there's one more thought here. This is just kind of like some background to help you see the relevance of this in real life. When I sum this up, what do I have? I simplify this. O3, which is what? Ozone, good, plus O. This is probably a free radical, like out in the atmosphere, yields what? two oxygens. Is this a good reaction to happen in our atmosphere? There's a balance, right? So we're taking away the ozone, so what are we making? Oxygen, which we need to breathe, right? Okay, so, but look at but like eventually the ozone, the hole gets much bigger above like what, the southern pole? I think it's the southern pole. We're all gonna die. So, the thing is, like, no, we probably don't want the ozone reacting with these free radicals to make more oxygen, because we probably have enough oxygen as it is. It's not like we're not having, there's a cycle, right? They're not consuming so much oxygen that we're all gonna like lose our air. But the ozone layer, they're gonna protect us from what? Like incredibly harmful UV rays from our solar oven above us, okay? All right, so I have 2 more examples. Go ahead and do 4. Write the rate law for this mechanism. What's the overall balance equation? What are the intermediates? Alright, so let's check our overall. It's on the board. We'll check them right here. So we've canceled out C4H9 cation, and then OH2 cation. Any other, what have I just canceled out? The intermediate. So who are the intermediates? C4H9 plus and okay, so those two cations. So we've made one thing that's not an intermediate. Who is it? Wait, who do we make that's not an intermediate? Bromide ion, right? So this is non-intermediate. It's probably just a waste product that's done and it's going to be floating around solution. It's not utilized to start the next step. Okay, are there any catalyst? No, nothing appears at the beginning and then at the end, so there's no catalyst here. Who is, who controls what is the rate law? Rate is equal to K concentration, okay, BR. Okay, so make sure you put your brackets to show concentration, so you're using this as your rate determining step. And then, yeah, we're good here, right? Yeah, question? Okay, so basically we know that this is the reactant in the rate determining step. And so the molecularity, meaning the coefficients, be that it's a 1 here, this is the coefficient that's plugged in as the order in the rate law. That's it. The coefficient is the order.
So if it was a 2,
Yep, if it was a 3, you put third order. If it was a 5, I've never seen 5, but if you had a fifth order, okay? Okay, that's the same as something else. I'm going to move that. this is the last one that mechanism-wise, and I have to show you this because it's a very special one. Notice on this reaction, I'm not sure I had the same denotions on 5. No, is this one on yours? Yeah, there were 2 5s, okay. So I put one thing different. Instead of just saying fast, I put on the bottom part down here fast equilibrium. Do you know why I put equilibrium there? Because you have a reversible arrow, right? So that means it could go both ways. Okay, so let me show you how to process these. Because you have one of these on your FRQs, the practice FRQs you guys have in your packet. So we have this reaction, we have the rate. Which of these mechanisms are the most likely a mechanism that this reaction occurs by? So what do we have to prove? Let's call this mechanism 1 here. And this will be mechanism 2. What do we have to prove about mechanism 1? Okay, so the slow step matches the VCE and the... Oh, okay, so the slow step molecularity matches the rate law designation here, and then the overall matches the overall. Okay, so what's this overall? Okay, so we've canceled this out. And canceling anything else? No, okay, so 2NO plus 2H2 yields. Okay, so I need somebody else to tell me, does this match? Okay, so 2NOs, 2H2s, 2NOs, 2H2s, and 2 O's. So check the overall BCE has been met, okay? And then does the slow step, meaning the rate determining step, reactants molecularity match the rate law? Yes. Okay, so this is a viable mechanism because there's a 2 here, so that's second order. There's a 1 here, and that's first order. So the molecularity matches. Okay, so now how about the next one? So this is viable mechanism 1. Is mechanism 2 viable? Let's check the overall first. Carrington, what cancels? Into
Yes.
N2O2? Okay. Oh, and 2O. Okay. And nothing else should cancel, so go ahead now. What's the fold?
So, 2NO plus 2H2 equals diatomic nitrogen plus 2H2.
Okay, so does this match the overall? I mean, you can't see it now, but this one did, right? So this is the same thing. Okay, so the overall matches. Okay, now what are you looking for? So here's the weird thing, right? So we have this flow step right after a fast equilibrium. So what's really happening here? There's a NO, there's a nitrogen monoxide, there's another nitrogen monoxide. Boom! They hit each other really, really fast, but they can kind of go back and forth to reform reactants and form products. There's an equilibrium process here, that's our next unit we're going to talk about. But once they collide, immediately N2O2 collides with what? Hydrogen. But that's our slow step. So it's taking some time, but it's still colliding, and that's going to be what's determining the overall rate of this reaction. So essentially, you know, here's the rate law that this step truly would be written as, right? K into O2 times hydrogen, right? And that does not match what we have above. But what basically you can do in situations where you have equilibrium, you can say that this is equivalent to this because they are occurring in such dynamic equilibrium. It's a very fast process. So essentially, you can substitute N2O2 in for N2O2, or 2 NOs in for N2O2. Okay? So if I do that, what does this become? 2 NOs. So then what does this become? NO squared to the second power. Okay, so does that match the rate law? Yes, it does. Okay, I need to show you the proof behind this, so write this piece down, okay? So I'm telling you orally you can substitute in, so yes, it would be a viable mechanism because the fast equilibrium occurs so quickly, it feeds itself into the step, that's the rate determining step. But what's happening here is essentially, we're saying that rate of the forward reaction, which is going forward, right? K forward, this is the rate law for this first reaction. And then these are the reactants. You got me here? I'm pulling this from this right here. I'm setting that equal to the rate of the reverse reaction, because it is able to reverse. It is an equilibrium step. Equilibrium just means that the rate of the forward equals the rate of the reverse. So that's essentially why I'm setting these equal. I'm going to set that equal to rate reverse. This is an R. K, and this is the rate law constant for the reverse reaction. The concentration of N2O2 first power, because that's only to the one coefficient. Okay, so essentially I'm saying rate forward equals rate reverse. That's the definition of equilibrium. That's why I can do this. So who cares about the rate? I'm going to pull the 2K items together. So K forward of nitrogen monoxide to the second power is equal to K reverse of dinitrogen dioxide to the first. Okay? And I'm eventually going to get to the point where I want to plug in, I want to sub in one of these concentrations for the other. So I want to find what this N2O2 concentration is by itself. So what do I need to do? Divide by KR, so K reverse, on both sides. Okay? So then dinitrogen dioxide is equal to a cumulative rate law constant. I'm just going to say cumulative rate law constant. I'm not going to call it KF over KR. I'm just going to call it K. K3, just to designate it's the third K I've kind of listed here, times NO squared. Okay, so what I had originally put for the rate law right here was what? K concentration of N2O2 times H, right? Okay, so what I want to do is I want to take this N2O2 and plug in what I had. Well, now I can do that because I've proved the relationship via the equilibrium step behind the scenes, but this is equivalent to this. So if I had N2O2 right here, I'm not going to put this in here, I'm going to put this in here. But the K's end up meshing and squishing all together. That's what we call a pseudo rate law constant again. So I'm going to call it K4. It doesn't really matter what I'm calling it, it's just K. It's just a constant. And this is NO squared, and then I still have the H right here, so I still have the H right here, or hydrogen gas. So this, does that match the the original rate law? Yes. So that's the proof behind it, but there's a substitution, which means that I can only do substitution when I have a fast equilibrium step. All right, we'll talk about that more, yeah. So that's the thing. Like I said, we cannot prove a mechanism. We can only look at the two criteria to say that this mechanism is this mechanism is viable for the reaction given. So neither one is better. They put both because we don't really know which is the correct one. Yeah.
If you substitute it or flip it, would that change how it matches the BCU?
If you flipped it, so I wouldn't substitute in the elementary steps because it might, but I don't think it would because this is going to cancel regardless. But if you flipped that, yeah, I would. But even if you substituted, I don't know, would you substitute this in here?
Like, because you're saying you would flip it because it's basically equal for the fast equilibrium. Would that like change how
That would change how the mechanism proof occurs. It would not be a viable mechanism. But I think if you substitute that in, it would be the same. So, all right, now I'm going to go to the part where I actually want you guys to practice. I think I got this now. Oh, I got to go over catalyst. But I'll go over that in a minute. Everybody, look at next door on your notes. Do you guys see a problem set that says 1 through 12? No, 1 through 6. No, 1 through 12. It continues. Okay. Let's work for 10 minutes. Let's see where we are in 10. So it starts right next to the notes. It says mechanism practice worksheet. It's got like a little capsule on it. I think it, let me double check. Just start on the one for me. I thought it was 12. I think. No, it's actually 13 because I think this number's right. Manipulate on the bottom of 1, 2, 3.